Okay, I think we should go ahead and get started. I'd like to thank everyone for coming to the. I'd like to thank everybody for coming to the last, and this is the 10th of our radio astronomy lecture talks. Before we start, we'd like to thank George Halborn, the late George Halborn, for his generous support of this series. Without this support, there would have not been such a successful series, and for those of us who've been to all the lectures, it's been great so far, and I know we're going to end on a high note. It's also been supported by Sierra, the Weinberg College of Arts and Sciences, and the Department of Physics and Astronomy. Today, we're very happy to welcome Chuck Bennett, a Bloomberg Distinguished Professor at Johns Hopkins University. Dr. Bennett went to the University of Maryland in College Park as an undergraduate before receiving his PhD from MIT in 1984. After receiving his PhD, he joined the scientific staff of NASA Goddard Space Flight Center and later became the infrared astrophysics branch head and then senior scientist for experimental cosmology and a Goddard senior fellow. Dr. Bennett later joined Johns Hopkins University in 2005. His major field of expertise is experimental cosmology. He has contributed to the establishment of the standard theory of cosmology and is now engaged in testing and extending this model. Dr. Bennett led the WMAC mission. Previous to that, he was a deputy PI for the differential microwave radiometer on the COBE mission. The scientific results from this work included the first detection of CMB anisotropy. He's received too many awards and honors to fully list here. To name a few of the highlights, he's a member of the National Academy of Sciences, a fellow of the American Association for the Advancement of Science, a member of the American Academy of Arts and Sciences, a fellow of the American Physical Society. Dr. Bennett has also won several prizes, including the Shaw Prize of Astronomy, the Gruber Cosmology Prize, the Comstock Prize in Physics, the Harvey Prize, the Henry Draper Medal, and the Tomasoni and Chisesi Prize. Today, he's going to tell us about the Standard Model of Cosmology with a somewhat different angle than the other two cosmology talks we've had so far. And remember to stay following the talk. We're going to have pizza come in. So join me in welcoming Chuck Bennett.
Thanks very much. It's a pleasure to be back at Northwestern. I think it was about 10 years ago I gave the physics colloquium, so it's high time I'm back again. And so the topic I've chosen to talk about today is the Standard Model of Cosmology. Do we have one? What is it? Just a bit of history here. The basics of the expansion of the universe and the prediction of the cosmic microwave background was made by Ralph Alpher. Here he is with Hermann and Gamow. That prediction was made right after World War II, and then the CMB was discovered in 1965 by Penzias and Wilson, and I think you all know that they won the Nobel Prize for that discovery. But the CMB radiation from the early universe is essential for our understanding of cosmology. It's our only real probe of the early universe. So astronomy or cosmology used to have a bad reputation with things that couldn't be measured, and that I think really pivoted when the COBE mission measured the spectrum of the cosmic microwave background shown here, and the temperature measurement was to 4 significant figures. Here it is recalibrated to the WMAP mission. So this is what I think was the first measurement in precision cosmology. Not, maybe a factor of 2 or something like that. So the fact that this is a black body tells us that the universe used to have matter in equilibrium, thermal equilibrium with radiation, and that supports the idea of a hot, dense early universe. The COBE mission also had the anisotropy instrument, which detected our proper motion through the cosmos on the dipole. If you take that away, you see the glow of the Milky Way galaxy, but real fluctuations outside the galaxy. That was the first detection of CMB anisotropy. Basically, it was a 2-parameter measurement. It was actually closer to a 1-parameter measurement, which is just the amplitude. The fact that we knew at what amplitude there was anisotropy. There was a little bit about the slope of the power spectrum, but it was so uncertain that it wasn't tremendously helpful. And then we have the WMAP mission. The COBE mission I just showed you had 3 frequency bands to separate the cosmic microwave background from foreground emissions. We decided that if we wanted to go deeper, we needed to have 5 frequencies. So here are maps of the sky and the 5 frequencies of the WMAP mission. These maps were published in 2013. And I don't know if you can tell, but the galactic signal reaches something of a minimum close to this 60 gigahertz, somewhere between 60 and 90 gigahertz. There's a minimum of the foreground emission, so that kind of frequency is beneficial for observations. So this is the temperature of the sky, or if you're familiar with Stokes parameters, Stokes I, but WMAP also measured polarization. So here are the 5 frequency maps in Stokes Q polarization, and again in Stokes U polarization. Here we go. Okay, those two can be combined to just a total kind of polarization in the color coding with the direction indicated by little white vectors here, and the bad news is that at the lowest frequency, you can see we've detected polarization over the entire sky. So in the temperature, the CMB fluctuations, fortunately for us, dominate over the galaxy in this, at this frequency range, at least over a lot of the sky, but in polarization, that's not true anywhere. So it turns out
So all this polarization is galactic?
I should have said that. Yeah, all of this is galactic polarization. So it's going to be more challenging to work in polarization from foregrounds. Now, the Q and U Stokes parameters here are an easy way for us to define polarization, but they don't connect well with the theory because partially you can think of it as that they're coordinate dependent. So it turns out that what you really want is to recast the Q and U in terms of what we call E modes and B modes in analogy with electromagnetism. So the E modes are the curl-free component, and the B modes have the curl component. So now you still have 2 orthogonal polarizations, but it doesn't matter what coordinate system I choose. So those are the rest of the talk I'll be referring to E modes and B modes as the 2 polarization modes, and they connect better with theory, and that different processes create these. So I showed you the maps of the cosmic microwave background from WMAP. Here's the power spectrum of the fluctuations from large angular scales on the left to smaller angular scales on the right. The black data points here are the WMAP data. The red curve is a model, and it was in 2013, the final WMAP results, it was the standard cosmological model. It's made up of WMAP, other CMB experiments, particularly ACT and the South Pole Telescope data, which fill on the stuff that you don't see back here, and it also includes measurements of the galaxy patterns on the sky with the baryon acoustic oscillations, and it includes measurements, local measurements of the Hubble constant. So all of that is thrown in. It produces this red curve. You can see it fits the data, the WMAP data, quite well, but it also fits the other data with 6 parameters. And there's different ways to rewrite the 6 parameters, but at least the way I've written them here, there's basically a density of baryons in the universe, density of cold dark matter, the amount of dark energy in the form of a cosmological constant. N sub s is the overall underlying tilt of this, like that. Tau is the optical depth to reionization, and the last parameter here is the amplitude measurement. So those are 6 parameters, and they define, in 2013, when this came out, they defined every measurement we could make in cosmology. They fit well, and they fit this well, so that would be what we would call the Standard Model of Cosmology. Just to give you a feeling for, or remind you about what's going on here, and why this is so convincing in terms of fitting cosmology, is that we understand the physics of what's happening. You have an overdensity, and it has until the time of decoupling to go from a maximal size down to a minimal size. That's this first maximum compression mode. And then there's a mode that had time to go, a smaller mode that had time to go down and back out again to maximum rarefaction, which is shown here, and then you have your second compression. So you're alternating peaks between the maximum compression and maximum rarefaction, And so this is oscillations of the photon baryon fluid ringing like a bell. We can also, we can derive from this the baryon density, which basically is the ratio of the compression to the rarefaction peaks. So that gives you a precision measure of the baryon density of the universe. The mass density is a little more complicated, but generally moves these things up and down. Basically, the more mass you have, the fewer baryons you have. You have more cold dark matter, you have less baryonic matter, and so that makes more or less amplitude of the ringing. The curvature of the universe is probed by us looking at the decoupling surface. So it's a geometrical effect of whether the universe in between us and the decoupling surface is lensing the radiation in or not so much. And so that moves this first compression peak left and right. And then underlying all of this, before the photon baryon acoustic oscillations ever happened in the universe, we believe the universe began in its very earliest moments with something that's approximately flat here, but could have a slight tilt. That's the NS I mentioned before, measuring that slight tilt, and again, some amplitude. And that is what comes out, we believe, of inflation or whatever happened very early on. And then the baryon acoustic oscillations have happened later. But baryon acoustic oscillations happen at a temperature of 3,000 Kelvin. So this is not exotic physics here. This is very classical physics, and it's easy to fit it, and it's very convincing when you have a fit that you sort of know what's going on. So just to walk you through a little bit of this, if you take the ratio of the heights of the first and second acoustic peaks, then you get the baryon density as I described. You can take the baryon density and the fit for the total mass density and determine the time when decoupling happened. And so that gives you a time. And then you can take the baryon density again, and take the photon density. That comes from the spectrum I showed you from FIRAST. It's a black body, you can derive the photon density from it. And those determine what the sound speed is. And so you can calculate a sound horizon at decoupling, a physical scale that's just the string theorists tell me distance equals rate times time. So this is sound speed times time gives you a distance, and so now you've determined a physical sound horizon of the universe. So the way I like to think about this is the WMAP was looking through the universe with a very long, thin triangle, and it's looking at the sound horizon scale here, and we know what that is because we know what these things are from the power spectrum. The angle theta A is the most accurately measured parameter, as you might imagine. You're just measuring the angular size of spots. That's one of the easiest things that you can do. And so we have this long, thin triangle, and then we have two choices of what to do with it. One thing we could do is assume flat Euclidean geometry, and then we can use the triangle to get the local value of the expansion rate. Or we can do it the other way around. We can take the locally measured value of the expansion rate and use the triangle to determine if we have Euclidean geometry. So we did both of these, and since it was all self-consistent, it didn't matter which way you did it. So that's the idea of what's being measured. Before WMAP had results, I had put together a compilation of results that existed in 2002, basically. So this is all the measurements that we had, and I put a gray band through this that was consistent with all the measurements. So that's sort of the state of knowledge of the CMB power spectrum in 2002. And fortunately, there was a paper by Wang called Last Stand Before WMAP, which listed the parameter values and their uncertainty that people thought we had before WMAP. And so we went from this to this. Now, I'm just talking about CMB data. I'm not bringing anything else into this. So if you view the 6 parameters as forming sort of a cosmological parameter volume in 6-dimensional space, the volume of that space shrank by a factor of 68,000 from here to here. So normally, if you have a theory and you tighten up the error bars by a factor of 68,000, you might expect the theory to show some flaws or to break or to need some modification. So what's fairly stunning to me is that this really didn't break in getting this kind of stress test, you might call it. And so my conclusion from that is that there's something about this standard model that's at least substantially correct. Maybe incomplete, maybe imperfect, but it certainly has to be substantially correct to survive this kind of stress test. Well, the results of WMAP combined with the measurements from the Sloan Digital Sky Survey of the galaxy pattern in the universe was declared the breakthrough science of the year by Science Magazine in 2003. And the breakthrough year was called cosmic convergence, the fact that we have a standard cosmological model that we can fit all kinds of observations with 6 parameters. And the article said that portraits of the early universe and the lacy pattern of galaxies in today's sky confirm that the universe is made up largely of mysterious dark energy and dark matter. They also give the universe a firm age and a precise speed of expansion. So basically they're saying this is all hanging together, and we know the value of the Hubble constant. Okay. So things are good. The Planck mission launches, and we're about to get a lot more data. Launched in 2009, has 2 instruments, a high frequency and a low frequency instrument, and did observing in 2012, 2013, and had major cosmological data releases in 2013 and 2015, and it's now been 7 years since launch. So needless to say, I was very anxious to see what was going to come out of the Planck mission, and when the data came out, my first glance at it and other people's first glance at it, what I heard a lot of people say was that the results were remarkably consistent with WMAP, which was heartening. Because I did have people telling me the WMAP maps were full of systematic errors and you couldn't tell what anything was, and those were all foregrounds. So the fact that a different team with different hardware saw the same thing was good. However, looking a little more finely than the broad brush, there were 2 kind of areas of tension that were pointed out early on. One is that CMB power spectrum I showed you, Planck had a similar one, but vertically offset by about 2.5%. And the other thing is that the Planck team said that the universe is a little heavier and older than we thought. So following on the Science Magazine Breakthrough of the Year, that we have a precision value of the Hubble constant, we have the Planck team saying, well, it's a little bit off. So I'm going to explore that with you. Here's a comparison of maps. It's not hard to see with your eyes that these 2 experiments are measuring the same sky and the same kind of pattern. So again, that's in that broad brush sense, that's very heartening and very important.
So this version has the galaxy taken out except for the parts that you had to mask out? Or?
Yes, that's exactly right. There's data, there's microwave data from the missions that we use to model and remove foregrounds, and we could have left stuff here that wasn't very high quality, but instead of just taking that away so you're not distracted by it. But as you can see, most of the sky looks, after some foreground subtraction, looks very similar. Again, that's good news. So, but together with my team, we decided to delve a little more into this, a little more detail to see what we would see. Planck radiometers don't have exactly the same frequencies the WMAP ones do, but there are some that are close. So we took close pairs and took differences between the maps. So there's a 30 gigahertz Planck radiometer, and we also have a Ka band, which is 33 gigahertz on WMAP, so they're close but not exactly the same. Because they're not exactly the same, some of the foreground signals going to leak through, and you can see it here. And we did the same with 44, 70, and 100 gigahertz. And so we saw some things here that we didn't expect. For one thing, you can see there's a dipole pattern here, and here, and here, and there's one here too. And what's really odd about that is that in this 2013 data release, the Planck team calibrated off the WMAP dipole. So you would expect that there would be no dipole left. So we were a little surprised there was still one there. And then, I don't know how well you can see it, but there's a ring here that comes down around here and down around here. And that's an extra feature on the map. And so the question is, what are those? That my collaborators here were Larson, Wayland, and Gary Hinshaw. And so we wanted to go ahead and pursue that.
Can I ask before you go on?
Yeah.
About those pictures? I mean, is it significant that it alternates red, blue, congruent. I mean,
Yes, no, it is. So that's, I'm continuing along those lines. We decided to take that residual dipole away here, and we also decided to do a foreground fit and get rid of some of the foreground so we could see more clearly what else was going on. And so these are the maps that we saw then. You can still see this ring here. You can now see a ring here too, which is not thin like this one, but kind of a wider ring. And as you were alluding to, we can see blue, blue, red, red, blue, blue, red, red, et cetera, which is better known as a quadrupole. So there was a dipole we didn't expect, and now there's a quadrupole we didn't expect. But if we now fit a dipole and a quadrupole and the foregrounds and mask out the strong regions, you can see things get better. You're still seeing this ring here even more prominently now, and you're seeing this ring here. There's actually rings in these two that are hard to see with the eyes. So now we're past the broad brush and really digging into to more detailed levels. The feature here, we believe, is due to far side lobe pickup in the Planck instrument. So this is radiation it's picking up not in its main beam, but in a side lobe beam that's causing that pattern there. This one is sort of unaccounted for, but we've now fit out the dipole, the monopole, the galactic mission, and a model that we made of the estimated far side lobe emission, and we see that things clean up a little better, but there are still systematic errors there, or presumably systematic errors. Of course, when you take differences, you don't know which thing the feature is coming from. So to help take that apart, we took all the differences possible of the LFI, the HFI from Planck, and WMAP. And so you can see that if you take, for example, HFI minus LFI, you're definitely seeing features here. So they can't all be coming from WMAP. And the features you see between LFI and WMAP and HFI, WMAP look different. So our conclusion from this is that these features are originating in Planck, and they're different between the LFI and the HFI instrument. So that helps figure out where things are coming from.
So the LFI looks better.
Yeah, the LFI generally had lower systematics. So the quadrupole that you asked about, it turned, I showed you the dipole earlier. The dipole is actually only the first term in an expansion. When you move, you get a dipole, but you also get a quadrupole. It's called a kinematic quadrupole. WMAP decided in its maps not to correct for that. Planck HFI also decided not to correct for that. Planck LFI decided to correct for that, but they made a factor of 2 mistake in correcting it. So I think we now understand where all of the quadrupole stuff is. So that, this was useful for ferreting out what was going on there. So that part was good. The dipole part is at least in part related to this 2.5% calibration offset. So we had the 2.5% power spectrum difference that remained. We had this mystery of why we have inconsistent dipoles if we calibrated the same one. We decided to check this inconsistency. Is this 2.5 power dependent on angular scale or not? And so we took the first acoustic peak I showed you and compared that directly between Planck and WMAP, and we found that there was somewhere between 3 and 5 sigma discrepant. So if you think about the dipole is the largest scale thing you can do, and it's perfectly matched, and the smaller scale stuff is discrepant, then it can't just be a constant offset. It's got to be an angular dependent offset. The Planck team suggested that there was a WMAP far side lobe uncertainty that we had not ruled out that could be responsible. So we actually went back in this paper and went back to our WMAP beam pattern data and far side lobe data and did an analysis for that specific thing, and we published that we could rule out that was a source of this offset. Okay, so we've talked about the maps, we've talked about the power spectrum comparison. How about the cosmological parameters themselves? So here's a bunch of parameters, and the only thing you really need to pay attention to is this last column here, and the question is how different are they between WMAP and Planck? So mostly you would look at that and say that looks pretty good. The worst difference is only 1.7 sigma, which normally I wouldn't make a big deal about, and that is for the parameter of the cold dark matter density times the Hubble constant squared. And so that's the worst case, which is discrepant at only 1.7 sigma. So the parameters, look pretty good, not perfect. Unfortunately, that's not really the right way to compare them, because when you WMAP or Planck solves for parameter uncertainty, it includes cosmic variance, the amount of accidental variance by our place in the universe in our view. And because Planck and WMAP are largely, but not entirely, observing the same sky, that really shouldn't be in there in a comparison. That's being too optimistic about, it's underestimating the tension. So we decided that we wanted to try to do this right, which turned out to be a much more difficult job than I thought when we started. But what we ended up having to do was generate simulations that approximated the full covariance matrix of the parameter differences, given that Planck and WMAP have different instrument noise, different mass of the sky, so we're observing not entirely the same sky, and we sampled different ranges of angular scale, different ranges of multipoles. So all that needs to be taken into account to know what part of the cosmic variance is common and what part is not. So we did that, and several months later we did that, and we found that, again, thinking about the 6 parameters as just occupying a volume in 6 parameter space, some blob, we found that the Planck 2013 and WMAP parameters as a whole were discrepant at 6 sigma. So they were highly discrepant, actually, despite the maps looking very similar to start with. So broad brush things look good, but when you dig in, something seems a little bit wrong here. So we wanted, provoked by Adam Rees in the office next door to me, who wants to know what all this means for the Hubble constant, he provoked me into trying to answer that question. And we ended up writing a paper called The 1% Concordance Hubble Constant, same author list. And we can use this to ask the question of how consistent are the different cosmic measurements, and is there in fact cosmic convergence, as the cover of the Breakthrough of the Year in 2003 said. So I'm very fond of this kind of plot, so I'll walk you through it and then show you a zillion of them. So basically, here's the Hubble constant. And here, at the time we published this, although there's now a revision, this was the Adam Rees's value of the Hubble constant, and this is the 1 sigma uncertainty range. He just dropped that uncertainty range so it's now 70% of what it is here. So spiritually, it's the same, but it's actually narrower now. The central value hardly changed at all. This complicated axis is a measure of the baryon acoustic oscillations. If you wish, you can think of that long, thin triangle I showed you before from WMAP and say this is their measurements of the angle. But there's lots of ways to look at this. Now, they measure at different redshift ranges. I am incapable of plotting more than one at a time. So I've chosen the most constraining one, the 0.57 redshift, but they actually have a series of these, and when we do calculations, we use them all, but I can only show you one at a time. So here's the idea. The baryon acoustic oscillations measure relative distances, not absolute distance. And so that's giving you this, which is independent of the absolute calibration of distance, which is this. So if both the baryon acoustic oscillation and the locally measured H0 were correct, you'd be at this point here, if they were perfectly in agreement. Otherwise, you get these sort of error ellipses. The cloud of points here is from WMAP. And this is this 68 and 95% confidence ellipses here. And the overall best solution is the open box. That's using everything. And so you get a value of the Hubble constant of 69.5 as maximum likelihood value. And you can see it's very good for the baryon acoustic oscillations. It's a little low from Rees, but it's not grossly low. It's 1.4 sigma. And it's right on the money for the CMB, which of course has a lot of the weight in the fit. But if I look at these, I would say, no problem. Sounds good to me. It's a miracle, right? I mean, you're predicting the Hubble constant from high redshift and measuring the low redshift, and you're saying you hit it within 1.4 sigma. I say, great, hallelujah. So this law looked good, and it tells you that, that the Hubble constant is very close to 70. So this is WMAP data only with the vanilla lambda CDM model. But now I'm going to change the data and the model. As I say, I'll go through these more quickly now. So here's what happens if I combine the WMAP data with the ACT SPT data, which is the smaller angular scale data. So you have CMB on a bunch of smaller scales. And basically what happened is this cloud got smaller and moved down and to the right. So it came down this way.
So you're adding that, all the data together?
I'm adding the WMAP9, ACT, and SPT, including their lensing data, all together in this CMB here. So it shrunk the cloud because there's more data, and it moved it down this way. So I should comment at this point that there's a well-known geometric degeneracy in CMB measurements. And so that's what's allowing this to have this elongation here. But the spacing of the peaks is not something that's easy to adjust. And that's why it's narrow in this direction. And note what you really want to do is move it this way, but that's the well-constrained direction. So the fact that it moved down a little this way is not very surprising. It would be more surprising if it moved off. But now this is the best fit overall. You can see it's still pretty good. It's 1 sigma in the BAO. It's 1.3 sigma in H0. And you can also see that there's sort of, once you're off the center here, there's sort of a trade-off between the BAO and the H0 measurement, whether it's pulling that way or pulling this way. And of course, when Reese shrinks the error bars, it's going to pull more down this way, which will raise the Hubble constant. So, that's why I like this diagram. You can sort of see what's going on with these different measurements. Okay, and now, yes?
So the open square, that's just the power spectrum data?
That's
before you've included all the ACT and stuff.
No, that's everything.
That's everything.
That's everything.
So then what's the
so
cloud?
The cloud here is CMB, and this black point is this is the CMB solution here. This is the favorite CMB solution. But if I'm doing nothing here but a weighted average, basically, a statistically correct weighted average of all this data. So if I take the CMB data, which wants to be here, and the H0 data that wants to be here, and the BAO data that wants to be along there, and do a weighted average, that's the point where they're overall globally happiest. Okay?
And those two ellipses are 68 and 95?
On the BAO and the H0, right. And the fact that WMAP data cuts through there, I think, is great news, right? And that's what you expect for cosmic convergence, right? Okay, so, and you don't really expect it to hit bullseye, I mean, statistically, but I mean, it could, but that's expecting a lot. Okay, so this is the Planck 2013 data combined with polarization from WMAP and ACT and SPT, and it's noticeably up and to the left. And one of the things that I'll point out that I thought was odd about that is when we included higher angular resolution data with WMAP, with SPT in particular, it moved WMAP down and to the right. So it's not per se just because it's higher angular resolution data, but that's the opposite direction that SPT moved. So now you have the best solution here, which I want to point out is not actually all that far away from these other solutions. Now it's 68.6 instead of closer to 70. It's not a world of difference, but it's noticeable. You can see the baryon acoustic oscillation likes this lower part of this Planck 2013 data, but you can also see this is not trading off like WMAP was between the two. This wants to pull them both down in the same direction. So this is now 1.8 sigma from this Reese-et-al value. It was at this point that Planck, when we were doing this analysis, that Planck announced that they had found a refrigeration modulation that was affecting their power spectrum at L equal 1800, and that they were going to have a modification. So that's the reason this is the last one of these you'll see with Planck data, because then I stopped and said, okay, I'll wait till they fix that and tell me what the answer is, because there's no point averaging it in until I know that. But I was interested in seeing what different models would do to the data too. So, and I'll run through these quickly. Here is a model. Usually we assume curvature fluctuations entirely as the standard model. Here's what happens if I allow isocurvature fluctuations as well. And not too much happens. It kind of moves down a little to the right. The Hubble constant is staying on 70. It doesn't really affect the Hubble constant very much. Here's what happens if I add uncorrelated. It can either be correlated or uncorrelated with the curvature fluctuations. Nothing much happens. Here's what happens if I add massive neutrinos. It pulls it up and to the left, but the overall average solution is still down here at 68.8. And again, you're playing around with this degeneracy along this direction. You are not moving it the other way. Here is running of the primordial spectral index, a derivative of it with scale size. It basically doesn't do much of anything. Here is a tensor to scalar ratio from gravitational waves. Again, it doesn't do a whole lot. Still Hubble constant of 70. Here is a combination of allowing running of the spectral index and tensor to scalar ratio. Where I'm adding, this is not a 6-parameter model. There's an 8-parameter model now, so there's more give on the model. But still, the favorite solution here of all this data hasn't moved very much. Here's what happens if I let the helium abundance in Big Bang nucleosynthesis change. Again, not much happening. Now, here's what happens if I don't insist on a flat universe. Remember the triangle I showed you when we assumed something about flatness. So basically, what this exaggerates the geometric degeneracy, so you now can be all along this line, but it's still extremely narrow in the other direction, and the peak likelihood for the CMB is here, and the overall solution is here, 69.4. Really, nothing much has happened in the overall. Here is if the dark energy is not lambda, but has an equation of state W that's not necessarily -1. Now what you're doing is you're decoupling the connection between the early universe and the late universe. So you're fuzzing out what the CMB is predicting. It still has this degeneracy line, and it still doesn't like this point. And the solution is still right around here. But you've played havoc now with the predictive power of the CMB for the low redshift universe.
Yeah, and what is the range for W from like?
It can be anything at once.
From negative to positive.
Yeah, it just needs to be able to fit the data. So most of those values won't fit the data. So, but it can be anything it wants to fit the data with an adequate chi-squared. Now here is now I'm into two tooth fairies. Here is not flat and not lambda, and basically you're just eliminating the ability of the CMB to determine things. But of course, because you're doing that, now this is just trading off the other two measurements, and the Hubble constant is 71.8. This is an effect. Massive neutrinos and W not equal to -1, again, two tooth fairies. And again, because the CMB has been fuzzed out so much, it basically is just using the other two. This is an effective, this is like if you had another relativistic species in the universe. Again, it fuzzes things out a bit. It still doesn't like this point, and the Hubble constant is still about 71.3. And then, okay, so that's the series of those things, just to give you some idea of what happens when you make those changes. So in this plot, I still have a Hubble constant down here, but now I'm putting the matter density of the universe here, and I'm showing you, I mentioned that I was just showing you the baryon acoustic oscillations for redshift 0.57. That's this stripe here, but now I'm showing you the others too. And I'm putting that on top of the CMB. So there's a couple things to say. You can see that the Z equal 2.34 baryon acoustic oscillations is as a whole offset from the CMB. That's the one band of the baryon acoustic oscillations that uses the Lyman alpha force, which is a more astrophysically complicated thing to use. So it's not wildly far off, but whatever that is, 2 sigma off or something like that. The gray here is just CMB data, WMAP9 plus ACT plus SPT, and then the white is from adding in the BAO and the local H0 from Reese. So this is the point where all of these different measurements agree. and with the tension, it's included in the calculation, but the tension with 2.34 BAO, and this is the solution you get. You get the Hubble constant of 69.6 plus or minus 0.7, which is really a pretty small error bar. And you get a matter density of 0.286, again with a pretty tight error bar. So this is sort of the concordance, convergence cosmology from all of this data. So just for...
Planck.
Okay, well, that's what I'm getting to. So just keep in mind that I've just shown you a whole series of things where H0 moves around a little bit, but it's always somewhere around 70, right? Okay, so then the Planck 2015 data release came out, and they included more data, and now for the first time they included their polarization data. They said they had a better model of nonlinearity, so the Planck had a ADD converter basically that had nonlinearity in it. The WMAP one was, we put a lot of effort, Steve Meyer at Chicago put a lot of effort into making very linear, but this one had nonlinearity. We found that the 2.5% offset went away, so whatever was done to fix that, and I suspect some of it has to do with the nonlinearity model and other things, worked, and that was gone. They fixed the kinematic quadrupole that I showed you earlier. The difference maps I showed you earlier are now improved, although you can still see with your eyes systematic errors there, but they're better than they were. In addition, they listed lensing data for the first time, and they included that in their analysis as a CMB lensing. And they gave a new value for the optical depth, which was lower than what they had before, which already was lower than WMAP. So that was sort of what the news was. Just to give you an idea, here's the power spectrum ratio from 2013 to 2015 Planck. So you can sort of see that's 2% there. So you can sort of see the 2.5%. You can also see it relative to the WMAP 9, which didn't change in between. So it went from the red comparison to the blue comparison. So it got a lot closer to WMAP in this 2015 release. But in the 2015 papers, the Planck team pointed out an interesting tension in the data. If they take their temperature and polarization data, they predict a lensing amplitude that looks like this blue curve, which peaks somewhere around 1.2. Now, the lensing amplitude is not a cosmological parameter. It is a physical thing that's equal to 1, which is why there's a line here. This is the correct answer to the lensing amplitude, and this is the implication from the temperature and polarization data, which has a pretty low likelihood at 1. And so this is why they were pointing it out. When they added their own lensing in now, it moved the curve down to a more reasonable value close to 1, where you've got a reasonable likelihood at 1. So the temperature and polarization data are predicting lensing that is somewhat off what it should be. I mean, that's what they're saying. So here's just another view of the same thing. These points here are from the lensing. That's the lensing power spectrum, and the curve is from the temperature and polarization data. And you can see the lack of the fit here. It actually, ironically, the Planck lensing data fits the WMAP power spectrum data really well. So I'll say something else about that in a minute. So in continuing our digging in, trying to figure out what's going on, we did two things. We decided to break the Planck power spectrum into two ranges, L less than 1,000 and L greater than 1,000, because L less than 1,000 was pretty much the range plotted by WMAP. And so we wanted to see, are they behaving differently? What is Planck getting for the WMAP range and for the other range? And the other thing that we ran across in doing this is that there's a program called CAM, which enables you to do these calculations of the parameter values, but it's the gold standard program, but it takes a long time to run. So there's another program called PICO, which is a approximation to CAM. It just makes, you basically use CAM to train it, and then it runs faster. But we found in solving parameters with CAM and PICO, which are the blue and the red, that they're quite discrepant from each other in these contours. I mean, so one's of an approximation to the other. They should give you the same answer, and they're not. And so one thing we discovered in this work is that the PICO results from the Planck team are just wrong. Whatever they did to train Pico to CAM was not done in the area of parameter space or whatever. I mean, I don't know exactly, but basically we concluded the Pico results really shouldn't be used. And then we can go ahead and do the comparison of the low L Planck in black and the high L in blue. So the question is, given that split in the Planck data, how consistent are the black and the blue? And for some parameters, they look pretty good. But here, for the parameter we talked about having the most discrepancy about, omega CH squared, they're off by 2.5 sigma. So I say the high L and the low L Planck temperature spectrum disagree about omega CH squared by 2.5 sigma. That's the way of saying that. If you include all 6 parameters, that gets washed out to about 1.8 sigma overall. Okay, so this is in a paper by Addison et al. from our group. So we wanted to understand what was going on, and one thing we wondered is if the uncertainty in the optical depth may be causing this difference. So we decided to let the optical depth float and see how the parameters change. And so for the most part, the parameters don't change very much from letting it float. So you have this gap between the high L and the low L solutions, but if you vary tau, you're not going to solve the gap. That's what this is showing. It gets a little bit better at higher L. You can see these things walking together at higher L, but it's not enough to solve the problem. So if anything, this data wants tau to be higher, but it's not enough to solve the problem. So the other thing was to look at this lensing amplitude and see what's going on with that. And so we looked at the parameters as a function of the lensing amplitude. And here's omega matter here, for example, or I could take omega CH squared. And again, the red this is low L data sitting kind of, doesn't care what AL is, but the high L data is walking down to meet the low L data when you get this A of L of 1.2 or 1.3, which again is not a physical solution. But the Planck team was pointing out that this is a useful way of seeing what's going on. But here's the Hubble constant. Again, for low L, it doesn't depend on AL very much, but the high L actually is going from a very low value of about 62 up to close to 70 for AL equal 1.3.
Can you give an intuition of why the lensing amplitude should be 1?
Well, if you just work through the physics, they're making a parameter out of something that isn't. So, I mean, that's just the physics of what it is. But what they're doing, the reason they're introducing it is to show you that whatever tension that is there is well represented by varying that, which tells you that whatever's going on behaves a bit like lensing behaves. That's the way I would take that. So if you're trying to wonder, as you might be sitting there, what's going on here, one hint is that it behaves like something like the lensing behaves. It doesn't have to be lensing, though. It only has to act on the power spectrum something like lensing does. So here's the high L data, the low L data, and the lensing data. And what you expect, since AL equal 1 is the physical value, you expect these 3 bands all to cross at AL equal 1. And 2 of the 3 cross at AL equal 1. And the odd man out here is the high L data. So remember, the low L data agreed with WMAP. The low L data, the lensing data agreed with WMAP. So the Planck low L, the Planck lensing, and WMAP are all in agreement. But the high L Planck data is off here by 2.4 sigma. So that's the quantification of what we were seeing before. And just to let you know, when I average the Planck lensing data only in with WMAP, no parameter value changed by very much at all. So it's very happy with the Planck lensing. And it wasn't because of lack of statistical power, because you could see in some of these plots, it actually succeeded in substantially shrinking the error bar. So it had the statistical weight to move the values, it just didn't want to. So I see no problem in inconsistency with the Planck lensing data. Okay, so is the Hubble constant consistent? Well, I've already showed in our final WMAP paper, we said that this was the value of the Hubble constant. I made a bunch of corrections for new data, revisions by Rees, whatever. It changed almost not at all to this value here. After all this new data, this is the 1% determination of the Hubble constant from everything that we knew of in 2014. And this is the 2015 Planck result. And these are significantly different. And this is the brand new paper about a week ago from Rees, and this is even more significantly different. So this is in the category of what I call not okay. So what's going on? And the answer right now I'll tell you is I don't know, but I'll show you a couple other things. So the red here is the low L Planck data. The black is the WMAP data. You can see they're right on top of each other. And the yellow here is SPT data, high L CMB data. So I've split the Planck 2015 data into the high L and the low L, and the high L is the blue contours here. So the Planck data is made up of the stuff in the blue contours and the stuff in the red contours, which are almost mutually exclusive.
So question at this point. You picked the L equals 1,000 to distinguish these two regions. Is that obviously the right place?
No, it's not, and I'll mention that. You're one step ahead of me here. But
Sorry.
yeah, no, it's great. I'll get to that in just a second. So, so if you just use the Planck data, you're getting a Hubble constant of 64.1 plus or minus 1.7 from this. And you're getting 69.7 plus or 1 minus 1.7 from this part. And so the L greater than 1,000 Planck temperature data is discrepant, you can see it here, with the BAO at 2.5 sigma. Now the Planck team also often says that their data is very consistent with BAO, and that's because they are averaging these two, and it's ending up somewhere near here. But if you separated it, it's the high L data is inconsistent wherever it was at. Let's see. So the 2.5 sigma with the BAO, and then 3 sigma from Rees, and that's before the latest Rees result with an error bar. Of course, WMAP and Planck 9, as I keep saying, at L less than 1,000 are fine with each other. SBT covers L's of 650 out to 3,000, beyond where Planck goes. And if anything, it pulls, as I showed you before, it pulls on WMAP down this way, the opposite direction. The SBT, this SBT data is about 2.6, 2.7 sigma from the Planck high L data. Okay, so this is just another view of this is again the omega matter versus H0 plot. Here's the BAO data, here's WMAP and low L Planck, here's the high L Planck, and it's just another view of the tension. One more view of the tension here. Again, this is BAO data. This rainbow is Planck data, and you can see with these reddish end of the rainbow, everything's fine up near 69. When you get to the blue end of the data, or below 65, it's not fine. It's not the same. So now to your question, after we did all of this, I mean, we chose 1,000, obviously it was a round number, and also roughly where WMAP cut off, but then we asked the same question you did, is that maybe this is just a fluke of having chosen that. So we said, well, what's a better number to choose? And what you really want to do, since you're fitting cosmology to the data set, is you want an equal statistical weight of the cosmology on both sides of the cut, or you won't get very good statistics on the comparison. So, so we figured out that the statistical lever point is 800 actually. So we did it all again with L equal 800 as a cut, and without going through the details here, basically nothing changed. I mean, this went from 2.5, actually got worse, 2.5 to 2.7 sigma. So it's not sensitive, as far as we can tell, to exactly where you cut.
But
Yeah.
The other thing I had in mind is whether you have two samples that are somehow distinct, or whether there's an overall smooth trend according to
Right. So I don't know the answer to that, but at least between those two cuts, we don't see. Right. So I just want to summarize that the omega c h squared is high by 2.5 sigma compared to the low L data. It predicts the phi-phi lensing power 2.4 sigma too high compared to the Planck measurement of the lensing. It predicts a Hubble constant 2.7 sigma lower than the SBT spectrum does. It disagrees at 2.5 sigma with the BAO scale. It's at tension with 3 sigma now, this number, I don't know, maybe 3.4 sigma with the new Rees result for the distance ladder. And so somebody on the Planck team said, well, 2 sigma is not a big deal. And I said, yeah, but it's not just 1 2 sigma, it's a lot of 2 sigmas. And I think to some degree, the fact that it's in tension with SBT, now you might be tempted to start thinking of new cosmologies, but if there's tension with SBT, that's not going to be a successful avenue. Now, if that tension isn't applicable for some reason, then, I mean, everybody's welcome to think of new cosmologies, of course, but that's not my first reaction to this. But I think the SBT is dragging, I mean, I know it's dragging on the WMAP solutions in the opposite direction as the high-L Planck is. So the obvious question is, are there systematic errors remaining in the Planck 2015 data? And I don't know the answer to that. I'm just showing you what I've done. This is a plot from Ries's paper, his recent paper, where he's showing his new H0 result here. This is the 73. He plotted here WMAP combined with a bunch of stuff here. Actually, if you plot WMAP alone, without that stuff, the point would be pretty much here with a bigger error bar. So actually, WMAP 9 and his data are consistent. They're not exactly on each other, but they're consistent. And then he plotted the Planck data down here. And you can see the distance between these two. Now, if I play a little bit with his diagram, I just added an extra 1 sigma so you could see where 2 sigma was. And I split the Planck data into the high L and low L parts. So here's the low L part, and here's the high L part. And I gave the numbers for them here. So now this is 3.7 sigma, actually, right now, as I say, in the category of not okay. That's pretty tough to explain by statistics. On the other hand, this part of the data, I mean, if I had to pick a Hubble constant number, it would be right about here, which is the number 70 or so, which keeps coming up no matter what I average in or how I change the cosmology. Okay, so looking to the future, we have this ground-based class experiment. I'll just finish up with this. That's looking to measure inflationary B modes, but also reionization for the E modes, which is important because we've seen now tension also with tau, which I haven't discussed too much. But I'm a little less concerned about that because we're going to measure it. We're going to measure it better than Planck, better than WMAP, and we're going to measure it to the cosmic variance limit as well as it can be measured. And I think we'll know the answer to that. Classes in the Atacama at 17,000 feet. It scans 70% of the sky every day. I know you've heard 2 talks from Page and from Karlstrom, I think. And you know about the BICEP 2 result. That was 1% of the sky. We're going to map 70% of the sky every single day. And we're going to do it at 4 frequencies. And what, if I've learned nothing in 30 years of CMB measurements, is that you want to modulate the signal that you're measuring. And that's what WMAP and Planck do not do perfectly for polarization. And what we really want to do, neither mission was optimized for polarization, but this is. And so we have a rapid front-end modulator. And just to give you a sense, here is the WMAP EE power spectrum here. This was the Planck one until the new paper last week, which actually moved it down. And this is just showing you the ability of class to distinguish between the 2 models. It's like not difficult. So class will do that. This is a plot that's a little complicated, but I'm quite fond of. This is the BB power spectrum. These are B mode levels of tensor to scalar ratio 0.1, 0.01 in blue and green. And the red is the B modes that come from converting E modes and lensing. And you can see there's a crossover, which is, I've drawn it as roughly about there. And so the B modes are dominated by lensing on the right and by maybe inflation on the left. Of course, we don't know what level these go down to, but as you get deeper and deeper, this line is moving to the left. So the large angular scales get more and more important. That's why class is designed to cover the whole range in which the inflationary B modes could be the dominant foreground. And as this limit comes down, this will only move that way. At the same time, we know about the foreground problems. We have the high frequency dust in the hundreds of gigahertz here. We have the synchrotron polarization at the lower frequencies here, and then we have a minimum. And so this is the minimum frequency, and you get more dust dominated going up, more synchrotron dominated going down. So class was designed to sit in the middle and sample both sides. So, and all the other experiments, they tend to be a bit clustered here, but your class is in a unique part of this parameter space, and I'm sure in the end we're going to want to use everybody's data together and figure out what's going on. But here is just a sense of the measurement of class of a B-mode power spectrum and the ability to measure the low L part, as opposed to most people are trying to measure around here. I will point out there is this double peak, the so-called reionization and recombination peak. So the recombination peak is what people are going after. But had we had a measurement up here at the same time as BICEP 2, it would have been obvious at the time whether or not we were seeing the kind of B-mode spectrum that we were expecting. So that's part of why I think it's important to do it. One other final point is that because class has the ability to break the degeneracy between the amplitude of the fluctuations and tau in a much better way than we have so far, it means that the class observations, even though they're not directly probing the neutrino mass like the other two you heard about are, will actually substantially improve the limits by holding down, anchoring the other end of the power spectrum. So it'll make about a 30% improvement of any detection or limit on neutrino mass. And here's class from a week and a half ago. 1 week ago, we had first light. So this is a very heady time for us. This is, I don't know if it's dark enough, but there's Milky Way here, lots of stars. This is at 17,000 feet. If it was light out, you'd see Alma. So that's class getting started. And summary, paradise lost. I'm sorry, we don't have a standard model of cosmology that fits all the data. I've showed you that. It's just not true. I keep hearing people saying it, but it's not true anymore. Significant disagreements now exist. Is it data quality? Is it fundamental cosmology? This is what we have to figure out. But I do think there's a bright future with additional data. I think we can still work on the data we have and learn more from it. And most important, though, is the new experiments that'll take us even further. So I'll end with that.
We had some questions during the talk. We have some time for a few more. If there's
So you say significant disagreements now exist, but from my understanding, for your talk, you only mentioned one particular experiment where the disagreements were heaviest, right?
Yeah.
And so, with the exception of that one situation, we are still in a situation where we have more or less an agreement about Standard Model of Cosmology?
Yeah, so the question, and this is something we were thinking through when we were doing all of this analysis, there's lots of possibilities of what's going on, and people suggested other possibilities. If you want only one thing to be wrong, there's no option other than the high L Planck, right? But there could be two things that are wrong, and then that changes the situation. So if you want to say what's the simplest thing, then you would say the high L Planck. You have to. It's the only explanation that requires you to just change one thing. But maybe BAO and something else is off. So I don't want to say it definitively because there are other possibilities.
Oh, how would you estimate a chance of some kind of a systematic human error? The Planck analysis still has some kind of error that hasn't been found yet.
Well, I guess I don't really have any way to answer that. The analysis is a difficult job, and there's lots of people involved with it. So in WMAP, I tried as much as possible to have two people do the same analysis independently and check against each other, especially using different techniques if possible. One of the problems here is the Planck data volume is so big and the processing so complicated that one of the techniques we relied on a lot of running Monte Carlos is very difficult, very challenging to do with the Planck data, because it's just so time consuming just to run this stuff through a computer. So I really don't know the answer. I'm not part of the Planck team. I'm not inside. I don't see how it works. So I don't have any good feeling for that. But I do think that if the data were fully released, and it's getting there, that the community could dig in and try to do things. But that's not trivial either. You've had 1,000 people spend years working on the nonlinearity model and the beam pattern model and all that. So it's not something you're going to do one afternoon.
But related to that, is it the attitude of the Planck collaboration that this next release is the final, we've done everything we're going to do kind of release, or?
I know they're working towards a release at the end of this year. So I mean, some of this I think is funding related. So I think they're approaching the end of their funding. Many team members have gone on to other things now. So I mean, this is what happens when you get. This is why I mentioned it so many years past launch, because people start drifting away. So I don't really know exactly what their plans are, but I do know that they're aiming towards a data release towards the end of this year. I think that's the plan. And I think that one is focused on the polarization, but it may have other things. I'm not sure. Yeah.
When you talk about L values of 1,000 or up to 2,500 or whatever you had, that says you know the directivity of the people who are reporting the data know the directivity of the antennas to an extraordinary degree, almost hard to believe degree. Can you, with your systematics, tell them where they might have systematic errors?
Mm-hmm. Well, so I don't actually think it's an extraordinary degree. You're right. With the finer angular resolution, a lot of things get harder, like
And you
localizing.
start getting lobes and
Yeah, but I don't think it's an extraordinary degree, really. I mean, Gaia measuring positions of objects is an extraordinary degree of micro arc seconds. This is not quite that bad. So what they do is they use the planets like Jupiter. It's a strong signal, and you have transits, and you can fix your pointing to that or extragalactic sources. So that
so they calibrated in situ with
yeah, no, they do a pointing solution.
scanned, scanning
Yeah.
optical objects.
Right. Now the side lobes are a different story. I think estimating the side lobes is a harder job to do. But the actual pointing direction is, in principle, it's not.
Okay, but the actual intensities would be.
Yeah. Well, one of the problems is that the Planck saturates on Jupiter. So WMAP calibrated our beams on. Well, we did it on the ground. We did it with the moon in the side lobes, but we also did it on Jupiter. And so every time we didn't do anything special, but Jupiter's in the way, so we survey it twice a year for 9 years. So we have 14 fields of Jupiter. And so we can use that to put together the beam profile of the WMAP beams. But Planck saturates on Jupiter, so they can use Jupiter for the outer beams, but they have to use something else for the inner beams, and then you have to stitch them together. And the stitching together inevitably involves some degree of error. So, but I'm sure they think that they've done this well. I mean, I haven't delved into any of these things. I mean, if as was suggested, I start delving into all of this, just bring me food and water every now and then for the next 20 years, because it's a huge job to get into these things.
One last question? Any last question? I said one. So what's the time frame for class in terms of when your first light, but then
Yeah.
this data going to be to the point where it can start being compared to some of these other?
Yeah, so I think we'll start having our first data, say, have a 1-year survey in a year, and then at least 6 months to analyze that, in my experience. So that's the earliest part. We're planning to survey for 5 years, so we'll have more and more and better as we go. We're putting a priority on the lowest frequency, which some people think is odd, but at the 40 gigahertz is actually where we most need data that will help. I mean, every other experimenter is saying, how soon can we get your 40 gigahertz data? So a quality 40 gigahertz map of the synchrotron would be extremely valuable. So it'll come in stages. It's a long-term prospect, but
Okay.
yeah.
Well, great. If there are any questions, let's thank Chuck one more time.